Exercise 1104, the normal distribution. Now, can we see we've got a histogram? It's very, very squashed. But if I draw a shape around that, that's what this normal curve is. Now, if we conduct a survey about, I don't know, heights of adults, for example, in this, what they've found, if they've done it for thousands and thousands of people, that we will have, if we do our column or our histogram, our frequency histogram, if you draw a curve just touching the top corners of each histogram, it will look like this, which is called a normal curve. It's called a normal curve because it's symmetrical. Symmetrical about the mean. See, the height of 170 would be the average or the mean height. So the graph of a normal distribution, so this is like a normal distribution, is a bell-shaped curve which is smooth and symmetrical about the mean or the average. The heights of a large sample of adults are represented by this frequency histogram here with a mean of 170. And as the sample becomes larger and larger, so if we ask thousands or even 1 million people, the histogram will become closer. So that's not exactly a perfectly symmetrical curve, but the more people we ask, the closer it will be to this normal curve, which is perfectly symmetrical. You could fold it in half. Okay, so when you see that, it's come from a frequency histogram. Now, many natural characteristics such as height, blood pressure, skull width, like your diameter of the head, for example, are normally distributed. So in other words, we can draw the results in a polygon, in a histogram, sorry, and if I draw a curve over the top of it, it will look like that. Okay? For any normal distribution, so if your frequency histogram looks like this, or we can draw the curve like that, if it looks like this, if it's perfectly symmetrical, the mean will be in the middle here, the mean will be in the middle, the mode will be in the middle, and the median will also be in the middle. So for a perfectly symmetrical distribution, mean equals median equals mode. Now, these percentages are very, very important. So, in prelim, you looked at, on your calculator, you worked out how to find the mean. In the preliminary course, you would have been given sets of scores, and you went on your calculator and you worked out, you put all the scores in and you were able to work out the mean, and you also worked out the standard deviation. Now, what is standard deviation? The standard deviation is the spread of scores from the mean. So let's just write that here, what standard deviation is. So standard deviation is the spread of the scores from the mean. So the spread of the scores from the mean. Now, and you learnt how to calculate that in the preliminary course, standard deviation. But what they find for a normal distribution, so for example, if your histogram, if you did your whole histogram for thousands and thousands of scores and you had a normal curve, what we find is that 100% of the scores lie under this curve, right? But you know how this is the really big area of the curve, just in the middle there? So if I look at just the middle section of the curve, so here is my mean in the middle, here is my average. If I do mean plus 1 standard deviation and the mean minus 1 standard deviation, you'll understand what this is when I do questions, all right? You will find that 68% of your scores lie just in that section of the graph, okay? You listening? Now, you will be given these numbers in an exam. If I look at the mean here and I go out to the mean plus 2 standard deviations, and the mean minus 2 standard deviations, you'll find that most of your data, which is 95%, or a lot of your data, is under that region of the curve. I mean, you can see, this is all your scores. But just from there to there, the mean plus 1 standard deviation to the mean minus 1 standard deviation, in that middle section, you've got 68% of your scores. But then if we go a little bit further out to mean plus 2 standard deviations and mean minus 2 standard deviations, 95% of your scores are contained in that space, under that area. And we can also do mean plus 3 standard deviations and mean minus 3 standard deviations. Now look at that curve. Look at this one. All of the data is under here. 99.7% of the data is between mean plus 3 standard deviations and mean minus 3 standard deviations. That means on the left and the right, you've only got the 0.3% left. So, you know, just to do mean plus and minus 3 standard deviations pretty much tells me about 99.7% of the population. It's pretty accurate. It's pretty good. All right. Now, you can see this all in one diagram. So, this diagram here will show the percentages under the normal curve in more detail. You know how the three numbers are 68%, 95% and 99.7%. Now let's look at this here. Girls, if the mean is the middle, and if I divide 68% in half, what's half of 68? 34. This bit here is 34% and this bit here is 34%. Are we okay with that?
Yeah.
If all of this from there to there is 95, watch what I'm going to do. If this from there to there is 95, I'm going to work out what these two little bits on these sides are. Now, I'm going to do 95 minus 68. Do you get it? If this is 68 from there to there, and this is 95 from there to there, 95%, I'm going to do 95 minus 68. And I'm going to divide it by 2 to get each little section on the sides. Do you see it? So what's 95 minus 68, please? 27 divided by 2. That's your 13.5% just there and there. All right, now, the last one. All right, just let me get some colour. This bit in red, that's just helped me work out this bit here and this bit there, or that bit there and that bit there. They're the red bits. Because all of that's 95, this bit in the middle is 68. If I go 95 minus 68 and divide it in 2, I will get each of those sections. Now, I want to work out the blue little bits from there to there, from there to there, or from there to there, same things, from there to there. Now, aren't those little blue bits the difference between 99.7 and 95? Bits, I do 99.7 minus 95 will give me the 2 blue bits, divide it by 2 will give me 1 blue bit. Do you get that? 7 minus 95 is 4.7. We're going to divide that by 2 and we get 2.35. And that's those 2.35% there. Now, you will only be given the 3 numbers, 68%, 95% and 99.7%. But once we start doing these in questions, you'll see how this works, all right? Normal curves, exercise 1104, question 1. You know the mean is always in the middle. That's the mean, which is x bar. That's the mean. Which one has the higher mean, curve X or curve Y? Which one has the higher mean? No, this might be numbers along the bottom. Yeah, Y has the higher mean. Like if this is a set of numbers, this could be 10, 20, 30, 40, 50, 60, 70, 80, 90. This is a number line down the bottom because, no, I'll show you what I mean. Let's say we have this number line and I've got 10, 20, 30, 40, 50, etc. Sorry, you can't see it. And here is the graph for product X or something. And here is the graph for product Y. Can you see the mean is always the middle? So product Y has the higher mean. So the mean here is 20 and the mean for this curve is 40. Do you get it?
Yeah.
It's like you've got a number line across the bottom. Yeah, they're on the same number line. All right. So which normal curve has the higher mean? Curve Y. All right. But if you see how this is a thing with an arrow, that is a number line. Even though they haven't given you any numbers. You just imagine numbers there. All right, now, let's look at question 2. Which normal curve, why are they called normal curves? Because they're symmetrical. Do these two have the same mean?
Yeah. Yes.
They do. But which one's data is more spread out? Z. So, W and Z have the same mean. Can you see that? They have the same mean. Which is X bar. Remember the symbol for mean? X bar. But Z is more spread out. Do you agree with that? It's more spread out. Now, what does spread out mean? spread, a measure of spread is the standard deviation. In other words, Z has a higher standard deviation than W, because W's data is more squashed. Pretend you've got column graphs, a histogram under here. W's data is really squashed. Now, when you think of it in terms of, remember those numbers? 68%, 95%, 99.7%. Just remember that if I go 3 standard deviations from the mean, let's say I'm going from here with my Z curve, I've got 99% of the data all in that blue shaded bit. Only 0.3% on the outsides. We'll be doing more with these numbers later. So for the next 3 lessons, we're talking about these numbers. 3 lessons. All right? So this is just the beginning. So all you need to know at the moment is that the mean is in the middle. If your graph is more spread out, it's got the standard deviation's bigger. It's deviating more from the mean. That's what deviate means, spread out from. All right? Now, question 2. Now, this is going to help you. Roofing nails, this is what we use. So let's say we're in a factory. Roofing nails are produced by a machine and the lengths are normally distributed. So I could draw the lengths in a column graph or in a histogram like that. They're normally distributed with a mean of 5 centimeters and a standard deviation of 0.01 centimeters. Now, this is really important. I don't know where I'm going to fit this, but I need to use this space over here. I need it all. So I always put my mean in the middle. And what's my mean? 5.00. Then remember under my curve, do you remember that curve? Then I have my mean plus 1 standard deviation. So I'm just going to go plus standard deviation, 1. Then I've got my mean plus 2 standard deviations. Do you remember the symbol for standard deviation? Do you remember it? No, it's this. Standard deviation symbol is, just do this one. That'll do. Oh, actually, they call it S. Do you want to call it just S? Just call it S. They're using S. Yeah, but we're doing this formula next lesson. On your formula sheet, it's got S is standard deviation. However, on your calculators, you do not use the S button for standard deviation, right? So here, you've got S for standard deviation. However, on your calculator, when you calculate standard deviation, you do not use S. You use this, yeah, well, it's not sigma, it's, this little green thing on top of the 6, that's sigma. I know you've seen sigma look like that, you know, you've seen that sigma looks like this. That's capital sigma. That means sum in Greek. But this is lowercase sigma. That means standard deviation in maths. Oh. That's called sigma, so is this. They're both sigma in Greek. But this is standard deviation. This is sum of. Remember how you've seen that sigma? When you're doing mean. Sigma fx over sigma f. That means sum. But this means standard deviation. So, the symbol for standard deviation is this sigma. However, on your formula sheet, it's S for standard deviation. Now, yeah. You may see it as mean. This is the mean plus 1 standard deviation, the mean plus 2 standard deviations, and the mean plus 3 standard deviations. Then we can have the mean minus 1 standard deviation, the mean minus 2 standard deviations, and the mean minus 3 standard deviations. I really should be putting x plus 3, x plus 2, but I can't fit it. Do you get it? Wait, 2 minutes. So, the mean is 5. The standard deviation is 0.01, so this is 5 plus 0.01 is 5.01. Do you get it? This is 5.02 because the standard deviation is 0.01. This is the mean plus 1 standard deviation, the mean plus 2 standard deviations, the mean plus 3 standard deviations. This is 5.03. Do you get it? Now back down here, this is 4.99 because it's 5.00 minus 0.01. This is a length of 4.98 and this is a length of 4.97. Now, if I did draw the bell-shaped curve on top of this, if you did check all the nails from this factory, Do you remember the percentages? We would find that what percentage of nails, sorry, this is a bad diagram, what percentage of nails are between 4.99 and 5.01? Do you know what I'm talking about? Look at the thing from the page before. What percent of scores lie between one standard deviation of the mean? 68. So 68% of nails have a length between what? 4.99 and 5.01. Do you get it? 4.99 and 5.01. That's that first section. So I need to get rid of all that bad diagram. Remember, then we've got the mean plus or minus 2 standard deviations of the mean. So from mean, 95% is from there to there. Do you remember those? So that's 4.98 through to 5.02. So 95% of our nails lie between those two lengths. And the last one, 99.7% of nails, that's got to do with 3 standard deviations, lie between 4.97 and 5.03 centimetres. So we're trying to produce nails that are 5 centimetres long. So 99.7% of the nails lie between the lengths of 4.97 centimetres and 5.03 centimetres. Do you get the idea? So this is a statistical, it just shows you the lengths of the nails. 68% of them lie between 4.99 and 5.01. Do you get that? All right? Side of a school is 40 kilometres an hour. Year 11 students measured the speed of passing vehicles over a period of time. They found the set of data to be normally distributed. When they say that, it means, yes, it's symmetrical, okay? With a mean of 36, so watch what I'm going to do. I'm going to draw my graph. In the middle, mean is 36. Then I've got, I really should write mean plus 1 standard deviation, mean plus 2 standard deviations, mean plus 3 standard deviations, mean minus 1 standard deviation, mean minus 2 standard deviations, mean minus 3 standard deviations. Do you get it? So the mean is 36. So this value here is 36. And the standard deviation is 2 kilometres. So let's go. What's 36 plus 2? 38. Do you understand why I'm adding 2? Because this is whatever the mean is. So I know that my mean is 36 and my standard deviation is 2. So mean plus 1, 36 plus 2, and plus another 2, plus another 2. Do you get it? In other words, girls, some people were going over 40. Can you see that? What's the mean minus 1 standard deviation? 34? Take away 2 again. Take away 2 again. Now, when I look at that graph, I can now start saying lots of things about this graph. I can say 68% of those drivers were driving. Now, I know this isn't answering the question, but what percentage of people were driving between 34 kilometres an hour and 38 kilometres an hour? 68% of the people. Do you get that? Because that's the number we know. The mean plus 1 standard deviation to the mean minus 1 standard deviation is 68%. That's 68% from there to there. You know, 95% of the drivers, do you see this, were driving from 32 kilometres an hour to 40. Do you get that? But we've still got a bit of a problem. I need to know what percentage of vehicles passed the school at a speed greater than 40 kilometres an hour. Now, I know it's these people up here. I know it's them. But the thing is, what I need to do, we need to go back to the page before. Are you ready? I'm going back to the page before. There was one thing that I haven't mentioned. I want to come back here to the first graph. You need to come back with me. Something here. You know how this is 100%? You know the 3 standard deviations, they don't do everything. There's still a small amount of the population that's not accounted for. Because this is only 99.7% from the mean minus 3 standard deviations to the mean plus 3 standard deviations. There still is 0.3% between there and there left over, 0.3%. Do you know where that 0.3 is coming from? Because it's 100 minus 99.7 is 0.3%. Now, if that 0.3% is shared between the left-hand side and the right-hand side, that's 0.15% there. That's not accounted for. And 0.15% there, not accounted for. But I need to show you something else. On a curve, if you come back here, this 100% is everything. This is the mean plus an infinite number of standard deviations to the right, and the mean minus an infinite number of standard deviations to the left. If this represents 100%, if I put a line right down the middle, can't I say 50% of my scores are to the left and 50% of my scores lie to the right? Do you get that? Now that's really important. Don't think that 99.7% is everything. It's not telling you the whole story. There's still 0.3%, which is 0.15% on each side that we need to talk about. All right? Does everyone have that? Now we're going to go back to that question. Yeah. Yes, good. So the 0.15, sorry, guys, is shown down here anyway. It's the rest of it. It's shown there. That 0.15, it was shown. But I didn't discuss it before. All right? But the main thing I need you to know is that half the curve is on the left of the mean, half the data is to the right of the mean. That's really important. Now that's going to help us with the next thing. Got it? All right, let's go back to the question and let's answer it. So this is what I need to do now. What percentage of vehicles pass the school at a speed greater than 40 kilometers an hour? So I need to know from here upwards. That's what I need to know. All right, girls. Well, there's a few ways of doing this. Can you just tell me what this bit is down here in blue? What percentage is that? Good. 50%. Can you tell me this section what it is? So that bottom, from the middle of the graph down, so if I just want this, if I just work out what this all the way down is, I can do 100 minus the blue bit gives me the red bit. So half the graph here is 50%. Girls, well, this bit here, yes, is half of 95. See, if it's 95 from there to there, you okay with that? 95 from x minus 2 standard deviations to x plus 2 standard deviations is 95. This is half of 95. Do you see that, girls? It's symmetrical. If I want to know from 0 to 2 standard deviations, this is called 0, the mean. From minus 2 through to 0 to plus 2 is 95. This section here is half of 95. So it's 95 divided by 2 is 47.5%. So, do we know what the red bit is now? If the bottom half is 50%, so is the top half. I could have done that. So silly of me. So all that section is 50% as well, right? All of that section is 50% as well. If this bit's 47.5%, this bit is the 2.5% over the edge. So it's 50 minus 47.5, which is 2.5%. 50% below, I could have just not done that and done from the middle up is 50%. I know from the middle to 2 standard deviations is 47.5. So the extra bit here is 50 minus 47.5, which is 2.5%. We're going to practice this for the rest of the lesson, for the rest of the double. Wow. Well, no, anyway, the next exercise is very similar. So every time we get a question, we're going to draw. All right? Every time we get a question, we're going to draw. A machine, a machine produces cylindrical pipes. The mean of the diameters of the pipes is 8 centimeters. So I'm just going to put the 8. That's the mean. All right? And the standard deviation is 0.04. So what's my next number? So this is the mean plus 1 standard deviation, the mean plus 2, the mean plus 3. You just got to do this every time. The mean minus 1, the mean minus 2. I'm putting the numbers on the axis instead because these, so that's what you do. Now, in the next exercise, we don't write mean plus 1 standard deviation, mean plus 2. There's something called z-scores, and this is just called 0, 1, 2, 3, 0, negative 1, negative 2, negative 3, so much easier. All right, but the z-scores does mean 1 standard deviation above the mean, etc. But we'll do that next lesson. So, 8. What do I write here? Anyone? What do I do? Yeah, 8.04. What do I write here? 8.08. 8.12. Do we get it?
Yeah.
Subtract 0.04, 7.96. 7.92, 7.88. Okay? So you've got to subtract 0.04, subtract 0.04, subtract 0.04, and then from 8, add 0.04, add 0.04, add 0.04. All right. The question is, assuming that you have a normal distribution, meaning, yes, I'm allowed to use the numbers 68, 95, 99.7, that's what it's telling you. What percentage of cylindrical pipes will have a diameter less than 7.96? So I need to know this bit downwards. All right. Now, that bit downwards, always, if you need to know from a certain area down or a certain area up, make sure you do your 50%. Now, what's the blue section? What percent? Great. What is, I could work out the red section. That's what I want, is the red section. But if I knew this bit in here, in black, I could work out what the red section is. I know from the middle down is 50%. What's this? I know that, very good. I know that from -1 standard deviation to +1 standard deviation is 68%. So half of 68 is 34. Got it? See how the diagram helps you? Later you just go 0, 1, 2, 3, 0, -1, -2, -3, much quicker. All right? But the crucial thing is that you know it's 50% from halfway down to the end, to a negative infinity. The answer is, what do you think? For the red bit, 50 minus 34.
16.
Yep. So your answer is, the red bit is 50 minus 34. Sorry, I'll do it here. 50 minus 34, 16%. All good? That's it. A.
Yeah.
The weights of 10,000 newborn babies, don't worry about the 10,000, we don't write that on the graph, in New South Wales are normally distributed, which means, yes, 68%, 95%, 99.7% applies. These weights have a mean of 3.1 and a standard deviation of 0.35. What do I do? Do you know what to do? What do you do now? So that's your mean +1. I'm just going to go +1, +2, +3. I don't want to write mean plus, all right? It takes too much time. -1, -2, -3. It is the mean +1, the mean +2, but it's just taking too much time, all right? What do I write here for the first one? 3 point what? What do you add? You add 0.35, so you get 3.45. You get need to add 0.35 to that. So just get your calculator, go plus 0.35, get an answer. Plus 0.35, get an answer, right? What have you got? 3.8, isn't it?
Yeah.
And 4.15. Then go back, 3.1, take away 0.35, 2 point what? Is it 75? Yep. And then take away 0.35 again. Is that 2.4?
Yeah.
And then take away 0.35 again. 2.05. There you go. When you look at that graph, you know 99.7% of the scores lie between 2.05 and 4.15. 95% of the scores lie between 2.4 and 3.8. 68% of the scores lie between 2.75 and 3.45. Half of the scores lie below 3.1. Half of the scores lie above 3.1. All right? Now, let's look at the question. How many of these newborn babies had a weight between 2.75 and 4.15? So what you need to do is break it up into sections. You need to break it up into sections. Now, it's always good to work out from 0 what you've got. So that's what I want in red. But do you think you could tell me this bit from 0, from the mean to -1 standard deviation? What's that value? Guys, this is what I got, 68. That's what I'm given, right? Then I'm given 95. This is the data you'll get. They're the numbers you have. And you have 99.7. That's the data they give you. I need to break up this into two parts. To work out the red bit, it's best to do from 0 to -1. How big's that? If -1 to +1 is 68, what's half of that? Yeah, so this bit's 34. Do you get that? No? Guys, if I know from there to there, don't worry about this here. From there to there is 68, half of it's 34. Now, how am I going to get from 0 to 3? I know from -3 to 3 is 99.7, so I halve it. See, this is what I'm doing over here. I know from -1 standard deviation to 1 standard deviation, it's 68%. So therefore, from -1 to 0, it's half of that. Do you get it? When I put -1, I mean standard deviations. I know from -3 to +3 standard deviations, it's 99.7%. So they're from 0 to 3 standard deviations. So I know it's what's half of that. So I now need to know from 0 to 3 standard deviations. 0 means no standard deviations. Guys, if from there to there is 99.7, if I want that bit, it's half of it. No? Half of 99.7 is 49.35? No, 49.85. 49.85%.
Wait, why wouldn't it be 50%?
Because you're stopping
It's the third
at
one.
4.15.
Oh,
It's the third. It's the third standard deviation. It's asking, guys, I need to know from 2.75 to 4.15. From 2.75 to 3.1, that's half of 68. Do you understand why it's half of 68? And then from 3.1 to 4.15, that's half of 99.7. Because 99.7 goes from -3 standard deviations to +3 standard deviations. I only want half of that. Zero's in the middle. I need half of that. So that's 49.85%. Girls, it's not going beyond 4.15. Otherwise, I would have put 50%. Do you get it? So it's half of, so we know from -3 to +3 is 99.7. So therefore, girls, you can always halve those numbers to do from 0 to 3 or from 0 to -3 standard deviations. So we add those two together now, and what do we get? 34 plus 49.85. So 34 plus 49.85 is, what is it?
83.
83.85. Yeah, great. But it says how many. That's the percentage. So we're not done. What do you think? So that means 83.85% of those babies. So what do? 83.85% of what? Of all the babies. How many babies were there?
10,000.
So times that answer by 10,000. See, girls, what the numbers 68, 95, and 99.7 are, there's percentages. Percentages of the entire population. So they've told you your population is 10,000. So you do 83.85% of 10,000. Do you get it?
83.85% out of 100%?
Yes.
Or
So to do 83.85% on your calculator, it's 83.85 over 100 times 10,000.
8,385.
Yeah, it'll be 8385, which is answer D. Because it's 83.85% of the population. So those numbers don't give you the number of people or the number of babies. It gives you the percentage of the entire population. So once you've got 83.85%, you need to times it by 10,000. So let's say we got the number 10,000. How many kids were bigger than 3.1? Half of them. 5,000. How many kids were below 3.1? Because that's the average. Half of them. 50%, which is 5,000. Sometimes in the question they give you the number, sometimes they don't. All right. Here, I'll just leave that there for a minute. Girls, do you know why I decided to break it up around the mean? Because it's easy, because that's what's the mean is. So you go, because you know the mean from -1 to +1 standard deviation is 68. So from 0 to -1 is 34 and 0 to 1 is 34. You always go from the middle. So from -2 standard deviations to +2 standard deviation is 95. So if I go half of that, from 0 to -2 is 47.5. And from 0 to 2 to +2 is 47.5. It's half of that. You always pick the middle point 0 or the mean to split it in half. Okay? Now, next question. A machine produces nails, and when the machine is set correctly, the length of the nails are normally distributed with a mean of 6. So here we go. Mean is 6. And the standard deviation is 0.04. So do you know what you're going to write? 6.04. I'm not interested in the last decimal place. I don't really need it. Well, you can put it in. Just put it in. 6.080, yes. 6.120. Then subtract 0.04. 5.960. Can you just check these, girls?
Yeah.
What would the next one be? 5.920. 5.880. So are we starting to get used to this? We put the mean in, we add the standard deviation once, twice, 3 times from the mean again, subtract the standard deviation once, twice, 3 times. This is +1 standard deviation, +2, +3 standard deviations, -1 standard deviation, -2 of them, -3. But it's the mean -3, all right? I don't have to mean -3, mean. It's just going to get too busy if I write that, that's all, with all of them. All right. The question is, to confirm the setting of the machine, 3 nails are randomly selected. In one sample, the lengths are 5.950. Where does that sit? I think it's here. What, wait, just there. 5.983. Where's that one? Here. 5.983, somewhere there. And 6.140, my goodness, out here somewhere, all over the place. So they randomly selected. So this is where the 3 nails happen to be. It then says, the setting of the machine needs to be checked when the lengths of 2 or more nails in a sample lie more than 1 standard deviation from the mean. Now here's the mean. There's 1 standard deviation either side. How many of those nails fit in there? Only 1. So the setting of the machine needs to be checked when the lengths of 2 or more nails in a sample lie more than 1 standard deviation from the mean. Does the setting on the machine need to be checked? Yes. So it's yes, because you can say that because 2 or more of the nails, so you tell me what they need to lie between. Because 2 or more of the nails must lie between what? Here. Between 5.960 and 6.040. That's justifying. No, you don't need the 0 on the end. So it does need to be checked because 2 or more nails must lie between those 2. And only 1 nail does lie between those. Only 1 nail lies between these values. And 2 lie outside. Do you get it? Only 1 nail lies between these values. And 2 nails lie outside these values. And you know what? The diagram is fantastic. It's a good enough explanation. Draw the diagram. Just put 2 nails. Nails must lie in here. Do you know what I mean? But I've got 2 out of 3 that are outside. So the machine does need. And it says justify your answer with suitable calculations. They're your suitable calculations. That graph. All right? And you can put this as nail 1. Do you know what I mean? Nail 1. Nail, is this nail 2? Yep. No, it's not. 5.983. Sorry, this is nail 1. That's nail 2 and that's nail 3. All right, so that's actually showing you where those nails are in relation to the diagram. All right.